All right. Why don't we get started? Okay, just a few reminders. There is a quiz, a test, on Wednesday in class right here. Those of you, I've already had one person contact me about an alternate time or alternative time. If you need an alternative time for some good reason, then you better tell me like really, really soon, all right? And if you need extra time, if you have a accommodation letter of some kind, we'd better work out when exactly that's going to happen as well. All right. First of all, before we get started, questions. I see that the attendance has recovered slightly from last week. I guess people have actually had a chance to sleep or something, I suppose. So that means you're all ready for Project 3, which came out over the weekend. There's also a homework 7, but it's not due this week. It's due next week, since we haven't covered some of the material that's in it. Let me see what else was there. Yes, the Project 3 skeleton will follow in due course, but in the meantime, there's plenty of thinking to do. And yes, okay, so questions? Fine, well then let's just dive into code generation. Now, I'm going to talk about a subject that we're sort of honoring or that you can honor in the breach in Project 3, namely sort of the canonical way or acanonical way that we do code generation in compilers, which is that very often code generation, that is generating the output from the compiler, is broken into two pieces. The first piece is the generation of code for some idealized high-level machine. We call that intermediate language, IL, there are various terms for it. And then the second part is, of course, taking that and producing machine code. Now, for our project, it's almost as easy to go straight through, but actually having this idea in mind sort of suggests ways that you might better factor your program. So the idea here, now there are some standard ones. For example, Microsoft has this common language infrastructure thing, which has an intermediate language in it, and a fairly elaborate one, actually. The Java compiler produces bytecode, which is, in effect, an intermediate language. It's a high-level machine. It's a high-level language. It has notions of classes and inheritance and stuff built right into it, which don't, assembly languages and bare machines know nothing from this stuff. But they have it built right in. And Python, for that matter, has an intermediate form, although it's unlike these first two, it's not standardized. That's just how they do it. Now, there are a number of advantages to this, as you see. First of all, it allows you to write one part of the compiler without thinking too much about what machine you're generating code for, and that's kind of nice. So you say, all right, at this point, I need these two quantities, and they're going to be integer quantities, and I need to add them together, and then I have to take the result wherever that is, and I have to do this to it. So if you don't have to think about specific registers and so forth, this is a good thing. It tends to make the code generation target, it tends to make the code cleaner, basically, at least the code generator, which is always nice. And the other nice thing about this is that you can use it as a way of sort of leveraging a bunch of different implementations out of the same code generator. So I can have, so the GCC compiler, for example, produces code for a fairly large variety of architectures. And the way that it does that is it produces intermediate language that is more or less the same, or at least very similar for all the different machines. There is some parameterization that goes on things like word length and so forth. But then from that, it has a number of code generators in back that will produce a variety of different machine languages. So the trauma of going from an IA32 compiler for C or C++ to say a Spark compiler is not all that great. You modify this back end, and you have to. It's true, you do have to make some other changes, but it's mostly the thing that mostly changes is this back end, and that's kind of nice. The other thing is that about IL is that it's usually, or intermediate languages, is they're usually a bit more suitable for doing additional manipulations. In particular, what is called incorrectly optimization. In other words, improving the program. So this is it's a good sort of strategy. So here's an example. Standard sort of example is although I don't know how often it's used in compilers, it's used in the Java compilers. And this is a stack machine. So stack machine has the property that we, instead of having registers, although we usually end up with local variables, which serve a similar purpose. Instead of having registers, we have a stack of values at any given time. And the idea is that you carefully order your operations in such a way that you push the operands for any given operation on the stack and then apply the operator, which pops the operands off and pushes back on the result. So 7 plus 5, as you see, we push the 7, we push the 5, we do the add. Now, this is nice. It gives us a uniform scheme. So in other words, you can have a convention in your code generator that says, whenever you call the code generator for foo, it will leave the value of the value of foo will be on top of the stack, and everything else will be unchanged, or something like that. So you can do that, and there are also a few other advantages. For example, the operator doesn't have to mention where its operands are, so the operator tends to be a bit more compact. If you're doing subroutine calls are nice because a subroutine call, after all, is put these arguments on the stack, call the subroutine gives you back a value, and you pop off the operands. So that's perfect. It fits right in there. That's great. So you can just you can throw in the return address to the subroutine that you're also passing. So that works very nicely. Now, it has, I don't have any disadvantages here. The problem is, of course, that it does not quite exactly match the underlying hardware, so there are some handsprings you have to turn. And there's also the fact that it's not necessarily the best mate for some of these optimization procedures where basically you do things like reuse variables. You use an operand and you don't really consume it or pop it yet. You don't want to. So you have to come up with something to do with that. Okay, so now of course another thing is you've got to be careful about how you represent the stack. If you represent it in memory, then you're getting these memory operations all the time. And although they aren't very bad, because as memory operations go, these won't be very bad because of caching. Because if everything that's happening is happening on the top of the stack, then that thing is going to be there, is going to be more or less permanently in the cache, sort of. And So things will go pretty nicely. But there's still a certain amount of an extra cycle or two involved in getting it even from cache memory. So a slight modification is as follows. We'll represent the top of the stack in a particular register. We'll call it the accumulator. It's a traditional name for this. And everything else will be on the stack itself. So we can perform an operation by computing its operands and pushing each one of them onto the stack as we go. All right, so we push each of the operands onto the stack, and then we compute we leave the last one in the accumulator. We call the function body, and it puts the result in AC and we pop all of the operands off the stack. So there you go. It's pretty nice. So to do an add instruction, what we do is we add the accumulator to whatever is on the top of the stack, and then we pop now the answer is in the accumulator. Now we pop that operand that we added off the stack. So that's pretty simple. And the thing is that after we've done this, after we compute an expression, the stack will be just as it was before, and the expression will have been, and the value of the expression will be in the accumulator. So here is the full computation of 7 plus 5. First of all, we push the 7, putting it into the accumulator. If there were already something in the accumulator, of course, we'd have to push it first. But we put 7 into the accumulator. That's sort of the top-level push, if you will. Then we push the accumulator because we're going to have to do the 5. We put the 5 in, and then we do that addition, and that puts the result 12 in the accumulator. We pop the stack, which pops off the 7 that we pushed before. The accumulator is now exactly the same as it was, and we have the result we want in the accumulator. The stack is the same as it was. Now we have the result in the accumulator. So that's pretty straightforward. Now, this is, of course, gives you another reason why it is sometimes convenient to push things in reverse order. And the result of that is that this is also nice for some of the instructions that you're doing, as it turns out. So if we do the assembly code, we can do assembly code like this, and it is a little bit more natural, perhaps, to subtract in that particular order than it would be otherwise. Now, we're going to have a little problem. I really should go through and try to straighten these notes out, but as you know, as I think I mentioned briefly, there is, and the tutorial on the IA32 also mentions, there are these two formats, the AT&T format and the Intel format for assembler. And the tutorial uses the Intel format. GCC can do either, but by default it uses the AT&T format, which you see there. And the effect of the AT&T format is that the target goes last, and on the Intel, the target goes first. So it's very confusing, but I hope we'll be able to keep that straight. The clue is that we designate the registers differently. Okay, so the assembly language code for this, to move something into the accumulator, we just do a move operation, Y into EAX. We then push the accumulator. There's a convenient push operation, or is it a pseudo op? I can't remember. On the IA32, that will just push something onto the stack. It has reserved basically one particular register as the stack pointer. Then we load up X. We do the subtraction, where we subtract the top of stack. So %ESP here in parentheses is the same as 0 off ESP. It's a base it's a base displacement operand, meaning that you take the memory at the top of that's pointed to by ESP, you subtract it from EAX, and then you pop the stack, which is you get rid of the operand on the stack by pushing the stack up, by pushing the stack pointer up beyond it. This, of course, is for an IA32. On an IA3264 or IA or IA64, you'd have presumably 8 bytes for the integer, but that's another story. Okay, so translation is now pretty straightforward if we're going to do this translation. And this is a wonderful, this whole thing is a wonderful example in thinking recursively, all right? Beautiful example in thinking recursively. So we assume that we make up our mind, we do the tie-level design, we say, okay, we're going to have this code generation procedure. Let's just call it cgen. We'll give it our machine that we're generating code into, just some random variable, it doesn't matter. And now what I'm going to do is, you may or may not need that particular operand, but I've used it here in these notes. So what I'm going to do is just to do the addition for a binary operation, I'm just going to generate the code for the 2 operands, and then I'm going to emit an instruction that takes my operand, the operator for binary operations, translates it to some machine instruction, and emits that instruction. Boom, we're done. Right? So that's a pretty nice thing. I think I seem to be missing the pop the other operand off, but you get the general idea. So this is a simple, this is a very nice, simple scheme. It's a postfix order tree walk, which is the sort of thing you might expect on a stack-based architecture. So there you are. It's very nice, and that's the sort of thing that you can do. However, this isn't all right, so that's a stack machine, and it's quite nice. Now, what happens if we don't have a stack machine? What happens if we want something that's a little bit closer to the real architecture? Well, for many purposes, including optimization purposes, sort of a more traditional approach is to use something like a 3-address code. This is to say basically a very idealized register transfer level machine language. So where all of the operations look like this. Target gets operand, operator, operand. Well, not all of the operations, but the binary operations anyway look like that. So you have addresses of the operands in the target. I put addresses in quotations because sometimes they can be immediate addresses. And very often, especially with the RISC mentality, RISC mentality, you will have some requirement that these operands be registers or immediates, so as to make the instructions always possible. And then we throw in a few other operands that we're going to need along the way. For example, you do have to access memory occasionally, so we'll have instructions for assigning from a register an immediate into a memory, for assigning from memory into a register. We'll have some instructions for doing a branch, and some instructions for doing conditional branches and calls, like that. So with this complement of operations, we can build just about anything, at least if we have a sufficient supply of operators. So by memory operand, I'm going to mean something like these base displacement things, like register indirectly off register 1 plus 4, or indirectly off the sum of 2 registers, or possibly memory as some label. In other words, memory at this particular fixed address. Now our operator looks something like this, or now our machine code looks something like this. Again, it's a recursive tree walk, post-order tree walk. We get our operands, and this time the result is a little bit different, or this time the assumption is a little bit different. Our functions will all have the form that we generate code to produce the value, my value, I'm assuming I'm an expression, and I return as my value, the value of this function, the compiler value returns where it put the result. So where do you look for the result? Okay, so what this is going to do is it's first of all going to find the left and right operands, get their values, and it holds in some abstract thing, an operand star, it holds the operand, the location that the code generator decided to put these things. Then we'll allocate some place to put the result. So I'll assume that there's some sort of internal thingy that allocates registers for me, and I'll take that result. And then I will emit an instruction that takes the left and right. I will emit some instruction that takes the operand, the operator that corresponds to whatever my binary operator is, the machine instruction that corresponds to my binary operator, takes the left and right operands and puts the result in the answer in result, and then that result is what I return. Mind you, I'm not returning the answer. I'm not returning the result of the addition. I'm returning the register, or whatever, the location, the abstract location that the compiler is putting that result in. So this is always very confusing. You will at least once during this project, at least especially when you're tired, you will forget whether you are actually computing the answer to the, or actually computing the runtime value or generating code, and you'll do something strange. And then you'll wake up and say, what have I done? And it'll be fine, okay. So this version of emit_inst produces 3 address instructions. Again, this is a very high-level sort of sketch of what's going on, pretty high-level sketch of what's going on, where I've sort of sketched one possible structure for the actual compiler code itself. In this, yes, okay, so we can go on to a slightly larger project. I must say, by the way, and you'll see this again when you see the skeleton, there will be a temptation that I think a number of you will fall into to scatter print instructions or output instructions, C++ IO stream instructions, that to generate your machine instructions. That you'll just scatter it through the code generator. So there will be many places where you do things like cout, whatever it is, less than, quote, addl, unquote, less than, blah, blah, blah. If you do that, not only will your program look like an unholy mess, but I will come down on you with a flaming sword when it comes time to grade your project. But you really want to put a level of abstraction. This intermediate code is an example, a fairly elaborate example of a level of abstraction, but you definitely want to keep your code generation programs like these things relatively neat, like this. And that means that you come up with the code generation utility, the low-level utilities, whether you're doing an intermediate language or actually generating an assembly language, you come up with utilities to make that possible. So we'll give you some hints in the skeleton, but you really should have that sensibility. In fact, in general, God, as long as I'm on this hobby horse, in general, maybe it's the post-teenage mentality, You don't pick up your rooms, but really, I think we need a more aesthetic sense of what it means for code to look neat. In the sense of not neat as in the sense of keen, but neat in the sense as a tidy. It's not so much that I want to dictate to you what that means. Is it would be nice if people were. It would be nice if you would look at a messy program and feel an internal shudder and feel unable to proceed any further until you had cleaned it up. That would be nice. It would be nice. You might not get the project done, but at least you'd not lose style points. So that's. All right, I'm sorry. I'm an old man. Sometimes I get into these rants. All right, so let's imagine a somewhat more ambitious example in which we've got this mini language. We have we have sequences of instructions. We have defs. We have a few operations like we have a function call down here. We have plus and minus, we have integers, we have identifiers, or variables that is, and we have a conditional expression. And so we'll just designate the first function as being the main function or something like that. And we'll just compute, so running the program on input I will mean calling that first function and giving it I as a parameter. So the assumption will be we build the code assuming that we come into it, when we come into that first procedure, we've got one parameter on the stack. So we have some sort of AST, like as in project 2 maybe, and we'll just go on with CGen a little bit. So actually, before we get into, all right, so let's just do one, and then I think we'll take a break. So, for example, in this mini language, one of the ASTs that you would get is the one for D followed by a semicolon followed by P, a sequence of statements, in other words, and in Python, this would appear differently, of course, but in this mini language, we can put it down to a single operator. And what you would do in that case is, well, it's something like this. We'd simply go through, we'd perhaps put a whole bunch of statements. Maybe we would do as we do in Python, where we actually have a whole bunch of statements all together in a single block or some such thing, or statement list. So but that's no problem. We'd simply go through, and all we have to do is for every statement in the statement list, we call the code generator. Period. That's it. That's pretty easy. It's kind of almost silly to think about it, but of course that's what you do. And again, you have this nice recursive structure in which we do the code generation for each of the children, without, you will notice, ever looking to see what kind of children we have. We just call the code generator. Integer literals, that's really easy. All they have to do is they don't have to generate any code. They just return whatever operand is, whatever the abstract way that you are representing a literal operand. So this function, when called, will return a whatever internal representation you have for immediate operands, and then whoever uses it will be the one that actually materializes its value. Okay, so and non-operand, why did I need non-operand? I don't know. I need non-operand for something, I'm sure. Oh, I see. That's right. Oh, the code generator for statements, that's it. Code generation for statements doesn't have to return anything, we'll say, or it returns none, so we'll just have that as the return value. Okay, fine. So that's started. We'll do the rest of the language after the break, but first I'll pause for questions. Yes, did I say question? No, you're just scratching your head. Okay. Still not awake yet, huh? Sunday night partying. Oh, I disapprove. All right. Well, let's take a break. Yes.
I had a question about Project 2. Why does you know how in the decals when we canonicalized them, say each module had a list of decals, other decals in that module.
Yeah.
Why does the order of that list matter?
Yeah, I suppose in retrospect it doesn't, except that that's what the project spec says.
Because I guess my group, basically up until the auto grader ran, we had done everything depth first search of the AST instead of a breadth first search. So if we saw a class, we would dive all the way down into the class instead of kind of doing a breadth first search, and it made the ordering of our decals be...
That shouldn't matter, because if you do, think about it, if you have, I have module consisting of thing. Okay, so the only decals that go in the module are the outer level decals from this. So I'm going to encounter those in the same order no matter whether I do it breadth first or depth first. So there must be something, probably there was something else going on.
The other thing we did was that we basically put off handling imports until after we had parsed the entire main program.
I don't think that matters either, because all of the modules get separated. The modules get sorted by into alphabetical order. So that should not have caused a difference either.
Anyway, I was just wondering if it doesn't matter.
I mean, I notice things like that, and when I see that sort of discrepancy, I dig in to see what's causing it. If it looks like something harmless, then I won't count it. But, I mean, that's why we don't just assign points automatically on the basis of how many autograder tests you pass.
Okay. All right. Thank you.
All right, let's get started again. So how would we handle identifiers? Well, an identifier is always in our ASTs is always represented by some declaration, decal. So there's going to be some in other words, no matter what your compiler is, there's presumably going to be some information associated with each instance of the identifier. That's what you do during phase 2. You're figuring out what each of these identifiers is, or what you know about them at compile time. So what you do is, or what we'll do is, we'll figure out a place to put the value of this identifier, of this variable. So we'll just allocate a result. And then we'll generate an instruction to move it, or to move the location, move stuff from the whatever its location is, wherever it is, into that register. So I'm not going to go into details particularly. I just say, well, we look at the declaration, and we somehow in that declaration has got some method somewhere that finds where exactly we've decided to store this thing, and that goes into, and then we'll return that as our location. So a pretty simple thing. So presumably that would return an operand that the emit instruction understands, and move it into the result. And then you return this result register. Now, perhaps you've already noticed that I'm generating registers left and right here. And probably if you've been looking, or if you've ever looked at assembly language code, you'll notice that most compilers don't use anywhere near as many registers as I'm generating. Well, that's an interesting thought. I'm glad you had it. Please keep it in mind. Okay, calls. Now this is this is a sort of a complicated one, but not really too bad. We just generate the parameters and in reverse order usually. So we'll assume that there is some sort of parameter parameter instruction in our virtual machine that does whatever this machine is going to do with parameters. I don't know if I just push them on the stack or something like that. In other, there are conventions. You are probably familiar with certain architectures that have, I think the MIPS architecture will have conventions about where exactly you put arguments, and they'll have the first few arguments can go in registers or something like this. Well, that's nice, but we'll assume that somehow, by some magic, the virtual machine handles all of that if it's going to get handled. Okay, then let's presume that we have an operand on our AST that gets the thing that we can call, and we'll call that and go for it. Okay, so so we get the thing that you're going to call, and then you just generate a call instruction, and you're done. You return. We'll assume that there is some location that calls use to put their return values, and we'll just put the thing into that location and return that location as the result of this call. So it's pretty simple. And you'll notice something interesting about this, and let me just point out a little piece of C++ or object-oriented lore. I have, instead of saying, for example, here, child sub, what is it in our project? Child sub 1, I think, for the argument list. And instead of saying child sub 0 for the thing that you're calling, I've abstracted these into some functions, get callable and get arglist. And what that means is that I should be able to use basically the identical code for doing all kinds of different calls. For example, binary operations are just in our version are just going to turn into method calls of some kind. Those aren't regular calls, so we actually have to do something a little bit different, but they are still method calls. And by having everything inherit from everything that might involve a call, inherit from some common node, or for some common parent type, we can actually have everything use exactly the same code. It's just that depending on whether you're a regular call, or a binary operator node, your get arglist and get callable will be implemented differently. This is the kind of thinking that you're doing all the time when you're thinking object-oriented design. How can I abstract what I'm doing and make it used in other places in my compiler, and defined in some central location, so I'm not constantly doing the same, reinventing the wheel over and over again in my own program. All right, now things get interesting because we suddenly have to do some branching and other stuff. It's no longer the simple expression generation. So no problem. We'll simply think about this. We want to do an if then else. So we'll assume that there is let's see, where is the get else part, blah, 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 mid instance of, oh, I see. So this is, oh, that's right, I'm forgetting what the if instruction is. So the if instruction was this simple equality test. We're assuming that all our ifs are some simple equality test. Things get interesting when you have to have something more than that. Okay, so what we'll do is we have the two operands, left and right, that we're going to be comparing with each other. We have a then part and an else part of this thing, and I'm just abstracting them as get then part and get else part. in this case. And since there aren't too many places where you have to do this, you might in your code actually be using child sub whatever. That also works. Okay, so what we'll do is first we have to evaluate the left and right parts because we have to do the comparison to see where to jump. So we generate this code here to see if they're not equal. And we'll generate a machine instruction that says compare the left and right parts, and if they are not equal, jump to some label that we have, some new label up here. And otherwise, so that's fine. And now at this point, we'll figure out where we're going to put the result, whether it comes from the left part of the then or the right part, and we will generate. At this point, we will generate the code to put the result of the then part into that result operand. So we will do the code generator, and we'll do it for the we'll do it for the then part. We'll do the code generators thing to generate code for the then part. We'll take the result, the location that it returns to us, telling us where to put the result. We'll stick that into the result register, and then we will generate an instruction to go down to the done label. And likewise, we'll do the same thing for the else part, and that will then fall through to this label, and we'll have some routine that sticks a label, sticks into the assembly language code foo : that label. Now, this is a wonderful example. You'll find yourself studying late at night trying to understand this example, and you'll say, "Oh, wait. If the else branch is, let's see, how does this work here? Oh, yes. Wait, he's forgotten to allocate a result register for the case where you're in the else part." Oh, no, wait a minute, wait. No, he hasn't, because this isn't being executed at execution time. This doesn't cause me to, this instruction here does not cause me, which instruction? This instruction does not cause me to jump down here to the else generation. It simply generates an instruction. Oh yes, okay, fine. So you'll make that mistake a few times. But these instructions all get executed unconditionally. And if you follow them through, you'll see that they generate the necessary code. And again, these abstractions that sort of create labels for ourselves, we assume that we have something to create a label for ourselves and so forth. I don't exactly remember what happened the first time I wrote this code, but I seem to recall that at the time I wrote it, I had not yet written and this is sort of from a version of the compiler some years back, same structure. I don't think I had yet written any of these instructions for new label and place label and so forth. I just said, well, I know I'm going to need them, so I just made myself a promise in the form of a .h file saying that I had all of these operations, and then I proceeded to use them. I think that's so much nicer than filling my code with cout instructions, with cout and less than instructions. Okay, and I think we might just be able to slip in def. It's pretty easy. We'll assume that we'll have to, it depends on the machine that we're running on. There will be some standard function prologue and function epilogue code. We've seen it, we saw it for back in the section where we were doing functions for the IA32. It involves saving the old base pointer and pushing the old base pointer someplace, and then the dynamic link, the old base pointer, and then finding a new one. And returning involves popping it off and doing the return instruction. Okay, so a def will simply be that we figure out the name. We have the name for this function. So we'll slap down that label at this point. We'll emit its prologue. Then we'll generate code for the body. We'll put whatever that will give us the result value back that it's returning. Remember, this is a simple expression language, so it doesn't have return statements. We'll put that result, we'll move that result into this return operand, wherever that is, and then we'll emit the function epilogue code, and we're done. So the epilogue will include the return statement and so forth. And then the result of a def is nothing, so we'll just return nothing as its answer. And well, pretty straightforward. Now, of course, we've sort of swept under the rug all of this business about generating the function prologue and epilogue. We can do that later, but this is the general form, and this is all we have to do for this particular def instruction. Okay, well, we can look at this next time, or you can look at it. This is an example of a translation according to these rules. All right, I'll see you on Wednesday, and we'll have a nice, fun time.